Welcome to this lesson on acid-base reactions, specifically focusing on neutralization. Neutralization is one of the most important types of chemical reactions you'll encounter in chemistry. It plays a crucial role in everything from medicine to agriculture. Today, we'll explore what happens when acids and bases come together, and why this reaction is so fundamental to understanding chemistry. A neutralization reaction occurs when an acid and a base react together to form salt and water. The key characteristic of this reaction is that it results in a solution that is closer to neutral pH when acids, which have a pH less than 7, combine with bases, which have a pH greater than 7. They balance each other out. This balancing act is what we call neutralization, and it's essential to understand that the products are always salt and water. The general equation for neutralization is straightforward. On the left side, we have our reactants, an acid plus a base. These react together to produce our products on the right side, salt plus water. This is the fundamental pattern that all neutralization reactions follow. No matter which specific acid or base you're working with, the products will always be some type of salt and water. This predictable pattern makes neutralization reactions easy to identify and understand. Let's look at a classic example: hydrochloric acid reacting with sodium hydroxide. Hydrochloric acid, or HCl, is a strong acid. Sodium hydroxide, or NaOH, is a strong base. When these two react, they produce sodium chloride, which is common table salt and water. The equation is HCl plus NaOH yields NaCl plus H₂SO. This is a perfect example of complete neutralization, where strong acids and strong bases react fully to produce neutral products. Here's another important example: sulfuric acid reacting with potassium hydroxide. Sulfuric acid, H₂SO₄, is a diprotic acid, meaning it can donate 2 hydrogen ions. When it reacts with 2 molecules of potassium hydroxide, 2KOH, it produces potassium sulfate, K2SO4, and 2 molecules of water. Notice that we need 2 molecules of the base to fully neutralize this acid because sulfuric acid has 2 hydrogen ions to donate. This demonstrates the importance of balanced chemical equations in neutralization reactions. Neutralization reactions have 4 key characteristics. First, they always produce salt and water as products. Second, these reactions are exothermic, meaning they release heat energy. You can often feel the container getting warmer during neutralization. Third, the pH of the solution changes, moving toward neutral pH 7. And fourth, when strong acids react with strong bases, the reaction goes to completion, meaning all reactants are consumed. Understanding these characteristics helps you identify and predict neutralization reactions. Let's look at neutralization from an ionic perspective. In the complete ionic equation, we can see all the ions present: H+, Cl-, Na+, and OH- on the reactant side. After the reaction, we still have Na+ and Cl- ions, along with water. However, the net ionic equation shows us what's really happening at the molecular level. When we remove the spectator ions that don't participate in the reaction, we're left with the essence of neutralization: H+ ions combining with OH- ions to form water. This is the core of every neutralization reaction. The pH scale is central to understanding neutralization. Before neutralization, acidic solutions have a pH less than 7, while basic solutions have a pH greater than 7. The goal of neutralization is to bring these extremes toward the middle. After a complete neutralization reaction between equal amounts of a strong acid and strong base, the resulting solution should have a pH of exactly 7, which is neutral. This pH change is one of the most important indicators that neutralization has occurred. Neutralization reactions have numerous practical applications in everyday life. In medicine, antacids use neutralization to reduce excess stomach acid and relieve heartburn. In agriculture, farmers add lime, which is a base, to neutralize acidic soil and improve crop growth. Industries use neutralization to treat chemical waste safely before disposal. Even in first aid, we apply neutralization principles when treating insect stings and bites. Bee stings are acidic and can be neutralized with baking soda, while wasp stings are basic and can be treated with vinegar. To summarize, neutralization reactions are fundamental chemical processes where acids and bases combine to produce salt and water. Moving the solution toward a neutral pH, these reactions are predictable, follow a simple pattern, and have countless applications in science, medicine, industry, and everyday life. Understanding neutralization is essential for anyone studying chemistry, as it demonstrates the practical importance of acid-base chemistry. Remember, whenever an acid meets a base, neutralization occurs, creating products that are more neutral than the reactants.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.